So in this talk, I'd like to offer my perspective of what could bring game-changing breakthroughs to the synthesis of quantum materials. And I should say, this is, in my view, this is a brainstorming opportunity. So I have not socialized what I'm about to say with anybody in the room. You maybe want to throw tomatoes, whatever. But I'm hoping that this is the right kind of thing for this workshop. So it all has to do with breaking synthesis rules. And let me start off by stating what we as synthesis people consider some of those rules, some of the famous rules as well as some of the infamous rules. So Professor Gibbs, of course, that you need to have free energy on your side. Bernd Matthias, famous inventor of quantum materials from Bell Labs, had 6 different rules for finding superconductors. And one of those rules was to stay away from theorists. Professor Pauling, of course, on radius ratios for finding new structures for stability. And although we've all learned the rules, I think a very important direction to go in terms of discovering new quantum materials with superior properties to any materials known is to break those rules. And I would like to describe that in the next few slides. So let's consider, first of all, Professor Gibbs's rule. It's a very important rule if you're trying to make a new material to have stability on your side. If you want to make a nice, perfect, large single crystal, you'd like to grow it quite slowly. You'd like to figure out what conditions they are. But maybe the material that you're trying to grow, the stable polymorph, is not the one that has the incredible properties. So in this, if this is the way that the Gibbs free energy is, maybe this is the one that's the exciting quantum material over here, and not that. Okay? How do we get to that? And I think we'll hear later on ways to tickle it with light, apply pressure. I want to mention a different one, and that's really to redraw what the system is. So the thermodynamic system, it's okay. I'm calling it breaking Gibbs's rule, but in truth, we still need to have free energy on our side. But the way that we're stabilizing this phase is to change the system. So the system includes not only the phase that we want, but also the underlying substrate. If you have such a redefined system, and you bias the free energy of this phase by this interface, you can indeed make it so that this is the stable system over that. It allows you, from a synthesis perspective, to still grow this phase quite slowly and grow it with high perfection. What you use as a substrate, though, is key. You want to use a material that is isostructural to the polymorph that you want, the polymorph that was metastable. So the additional terms that come up in looking at the free energy here are the interfacial energy, the strain energy. So you want this material that has the same motif to also be well lattice matched. And the surface energy of this entire system compared to this entire system. So this is epitaxial stabilization. And this is a great example of breaking the rules. And if I went back and looked through the history of this, and Praveen Chowdhury, who many of you might know, David certainly knows him. When I was a postdoc at IBM, he was the head of physical sciences. He was the oldest person I know to start talking about epitaxial stabilization from a rigorous thermodynamics standpoint. And I'll show you a slide of that in just a second. But here, the idea is to exploit the combination of a film in contact with a substrate. And I'm going to come back again to this theme again and again, because as a synthesis person, I happen to be a thin film person, but many of you that do synthesis are bulk people. And I think there's an opportunity for more interaction between those communities. Those tend to be separate communities. We all have our different ways of making materials. But what I want to start the discussion on is what a huge opportunity it is to have the substrates and films come together to access hidden ground states in quantum materials. So here's Praveen Chowdhury, and he indeed says, the researchers attempt to choose the substrate. Well, this was in the days where there weren't that many substrates available. In fact, I'm sorry to say that we still live in the days when there are not so many substrates available. And that's really the opportunity, because although this was pointed out decades ago by Praveen, the rate of the pace of change here has been incredibly slow. And I think lots of opportunities remain to do this. So let's look at one system where there are perhaps the most substrates available, and that's the perovskite systems, a rich area for quantum materials. And up here on this side of the axis, I show some of the some interesting complex oxides, including some quantum materials. And on the bottom side, different substrates, different commercially available large single crystals to grow those on. You can see that there's quite a variety of substrates. And for a source of example, let me choose one particular quantum material. I'm going to choose barium ruthenate as an example. Okay, now barium ruthenate exists, and if you ask Mr. Gibbs what the stable form of that is at atmospheric pressure, it's this hexagonal structure shown over here. And the high pressure people have been having lots of fun with barium ruthenate and accessing these hidden ground states, this one at 30,000 atmospheres of pressure, this one at 50,000 atmospheres of pressure, and most recently, this one down here at 180,000 atmospheres of pressure, done by John Goodenough recently. And in this cubic form, indeed, the magnetic properties have changed. So this becomes ferromagnetic. It's got a transition temperature, which Goodenough shows quite nicely. And you might ask the question, well, what's happening to the underlying band structure? What's happening to the electronic structure of barium ruthenate? Well, although it's been synthesized by using this trick at high pressure, it's difficult to look at what the electronic structure of the material is directly. And that's an opportunity that I want to describe by combining these approaches of thin film and bulk. And so here I'm showing some unpublished results, but basically using a substrate, I'm not saying this is by any means the best substrate, but if we want to stabilize this cubic polymorph, we're going to put it on top of this cubic perovskite substrate. And this is lattice mismatched by a huge amount. Okay. The other substrates I showed you a second ago weren't cubic, so it has its own. But this one is cubic, so we have no octahedral rotations here. You can stabilize this for very thin films. Okay, so less than 5 unit cells, we've been able to stabilize this metastable polymorph, something that takes in bulk 180,000 atmospheres. You can do it in thin film form with the proper substrate. And indeed, if you look at the transport properties of our films, these are all different polymorphs. If we look at the cubic polymorph that we've made, this metastable one, you no longer see this cusp in resistivity versus temperature, which is indicative here of a ferromagnetic phase transition. It's quite flat. I'll come back. Here you can start to look at the electronic structure. So I'll show you more examples, angle integrated in just a second. But actually compare the electronic structure to theory. So for a modestly correlated material, to start to see what those differences are, and have important feedback to our theory colleagues who are trying to better understand quantum materials. You want to provide feedback in the same language in which they calculate. If they calculate the electronic structure, you'd like to feedback with what the electronic structure really is. Okay, now I'm going to come back to barium ruthenate in a second, but let me come to what for some, maybe in Bell Labs' time, this was certainly for Bernd Matthias, this idea of staying away from theorists. I think that's you couldn't do anything worse than do that. So obviously we want to break that rule, and I would suggest for experimentalists, particularly on the synthesis side, to team up with theorists and provide them with feedback that's useful to their theory. And I also have a challenge for theorists, which I'll get to toward later on in the talk. But to go further, not just teaming up with theorists, but teaming up to see where the atoms are really in the structures. So to team up with diffraction people, electron microscopists, to see, are we getting the atoms in the desired locations, what kind of defect structures there are, how to improve those from the synthesis side, as well as the electronic structure. There are great techniques that have been developed to look at the electronic structure, but they've been limited in their applicability to a very small set of quantum materials. And it's that I think there's a huge opportunity to break. So combining synthesis together with techniques, for example, in situ ARPAs or in situ spectroscopic imaging, STM, to globally or locally determine the electronic structure and be able to make comparisons to theory. So let me come back to this idea. Okay, so I would certainly break this rule and provide them with useful feedback. And a particular one that I want to show examples of, but this is not all inclusive, this is just one example, is the combination of synthesis with ARPAs. So in the world of complex quantum materials, together with my colleague Kyle Shen at Cornell, we were the first to do this in the world. And I want to show how that can change the perspective of quantum materials synthesis by having this combination with ARPAs. So if you think of the entire the world of quantum materials, it's it's what you can make in terms of what you can make by bulk. It's say this dot here. It has some very interesting materials in it. And then which of those can you actually look at the electronic structure of by ARPAs? Well, not only do you need to make a high quality single crystal, but that material needs to cleave. Because the way ARPAs is extremely surface sensitive. So you need to have a material that you can put into ultra high vacuum, and then in ultra high vacuum cleave it so that the surface doesn't get dirty, and you can have good electronic structure of it. Well, that's a small subset. Maybe I'm being too generous in what I'm showing you. And the same thing is true also if you're doing spectroscopic imaging STM or other techniques that look at these quantum materials. So you're limited to a small subset. Let's imagine this approach, which I think is today's approach, to a different approach. And that approach combines thin film synthesis with substrates, with in situ techniques to look at electronic structure. It's a much larger universe. And the reason that the universe is so much larger is because, first of all, we can do epitaxial stabilization. And let me emphasize that this epitaxial stabilization game is not something that the thin film people can do alone. It's not something that the bulk people can do alone. It requires this partnership. One needs a substrate that has the same motif and is well lattice matched to the particular ground state that you're trying to stabilize. That takes a willing and eager partnership between these groups to access this. So many of the games that can be played in thin films are metastable. So those things you can't make in bulk form. You can't strain things to huge amounts in bulk form. You can't make these metastable superlattices. But by this combination of being able to make these ground states and be able to play thin film games, here's another example, to be able to have juxtapose competing ground states between the film and the substrate. Dimensional confinement. So all of these games become possible in quantum materials and drastically increase the space. I've indicated some particular materials to these, some famous quantum materials. Okay, so here we have, LAO, STO, making use of the polarization discontinuity here. Here's a topological insulator example, combining with a ferromagnetic ground state on top of a substrate. Here's strain engineering that's given rise to this, what's a much higher superconducting transition temperature in iron selenide. I would argue that these are just the tip of the iceberg in terms of doing this, because these communities typically don't work together. And the examples that you see are what substrate they could get off the shelf combined with thin films. But if instead we were deliberately targeting materials and saying, okay, I need this particular pattern of octahedral rotations and this particular lattice constant, what are the bulk choices to synthesize, to go after that are thermodynamically stable, and then put a thin film on top of it? One can, in a very targeted way, investigate new quantum materials, and with proper in situ imaging, things like ARPAs or spectroscopic imaging in STM, to see what the electronic structure is on that system as well. These quantum materials and oxides are famous for all the hidden ground states. We heard that in Dimitri's talk just a minute ago. Here I want to just show what our theory friends see inside the computer when they look at one of these systems. So these are DFT calculations, okay? But my point is, notice how close in energy these different hidden ground states are. So this energy, this is the stable one here, okay? And this one is just 4 millielectron volts per iron away. It's within the accuracy of the DFT calculation, which, for quantum materials is not great. But I just want to show all these different ground states are waiting to be accessed. They're hidden from view in terms of having the stable one. And a way to access them is to target substrates to access their properties and then look at their electronic properties. So let's come back to this example of barium ruthenate. This is just an example. It's not published, but I just wanted to show some real data. Here's a look at the ARPAs of this hidden ground state. Okay, so this is a material that's not the stable form. It's been stabilized by using a substrate. And by having a pristine surface, okay, I should mention that even if you at 180,000 atmospheres, even if you could make a large single crystal, it doesn't cleave, okay? But here, in making a thin film of it, we stabilize the polymorph, and we have a nice smooth surface. So by looking at that in situ and not exposing the surface to air, we can look at the electronic structure, and we can compare the electronic structure to first principles calculations. Here with various methods, and you can add spin orbit, whatever you want, and start to see how it is that the band structure agrees and disagrees with what's calculated for these quantum materials to try to make our calculations better and better understand quantum materials. So as I see, this is a huge, it's a vast universe. Okay. So here you can see in terms of looking at these as a function of thickness that they seem like they agree fairly well in terms of the Fermi surface with these first principles calculations. But then when you look at the energy cuts, you can see how they disagree quite a lot with those. So if we want to make progress in better understanding and having better theories for these correlated systems, I think it's imperative to not only be able to calculate electronic structure, but be able to compare it to electronic structure on those same materials. Okay, so that was an example in the perovskites. There's a lot of exciting quantum materials in other systems. So in terms of wild semimetals, the pyrochlores are a great system. So let's play the same game in the pyrochlores. On the top of the number line, I show some of the exciting pyrochlores that have been talked about. We saw some measurements from Dimitri a few minutes ago. How about the substrates? Well, there are no commercial substrates for pyrochlores. Zero. And the same thing is true in many other systems that are of interest for quantum materials. That's the whole point. But it doesn't mean that they can't be made. So here is some nice crystals made by Darrell MIQM. He made these beautiful pyrochlores over here. Okay. These are all made by the floating zone technique. They have different lattice cuts. That's great. You can start to imagine playing those same games that I was showing you, that the thin film people can't do alone and the bulk people can't do alone. But together, things like strain, making metastable superlattices and heterostructures, and looking at what the effect is on the band structure of these quantum materials and measuring it could be possible. Okay, so I think that there's a huge opportunity to break Matthias's rule and provide, not only work together with theorists, but provide them with meaningful feedback for their theories to better understand quantum materials. Let me turn next to Professor Pauling and his critical rules for finding new stable structures. Okay, we've all learned this in Synthesis 101. I went to the ultimate source here. I went to Wikipedia, and you can see that in Wikipedia they tell you that if you're trying to make something stable, it's very important that your anions do not overlap. You get a lot of repulsion from that, and so this is unstable where you have a cation rattling around inside this cage. When you're doing this combined substrate thin film game, it becomes possible to violate that rule and actually make it so that you can have cations rattling around inside cages. And that can be extremely useful. So having a cation that rattles around inside of a cage allows you to break inversion symmetry. So maybe you want to have a superconductor that lacks inversion symmetry. Maybe you want to have ferroelectricity, multiferroics. All sorts of examples where you would love to have cations rattling around inside of cages. Sometimes, from the luck of nature, you have such a system. But being able to engineer it by having a substrate that stretches this box So instead of having this cage right here, imagine having a substrate that's a little bit larger than the spacing of these. That makes it so that the oxygens around this cation, I've shown here in green, you can stretch that box out. And if you stretch that box out, now it's possible for that cation to rattle around inside the cage. Okay, or if you squish, if you have a substrate that's slightly smaller lattice constant, okay, now this cage gets longer in this direction. Next thing you know, it's rattling around in this direction. You've gone from a case that was centrosymmetric, which destroys a lot of properties, to something that has lower symmetry, in which you can turn on properties and access hidden ground states. Okay, now that's just, whoa, I pushed a bad button. Okay. Let's, so let me just show you an example of that. So this is an example. Okay, so here's a nice, boring titanium sitting in the center of this cubic strontium titanate, a more boring textbook dielectric. But if you stretch that box, the titanium would like to rattle around inside the cage. So from an energy perspective, the energy landscape of the titanium looks like this. It looks like a double weld, classic for a ferroelectric. The other direction, the titanium can rattle around in this direction. So it looks like this double weld. That was realized by these theorists. They made a bold prediction before any experiments were done. And sure enough, it's true in experiment too. So you can you can access the hidden ground state. You can make strontium titanate, which normally in bulk is not ferroelectric at any temperature, and you can access the ground state and make it ferroelectric at or above room temperature, as shown by these experiments. So just an example of the power of bringing together the thin film and the bulk synthesis communities, and to exploit the interfacial energy from substrates. I want to show another example of this in quantum materials. So the strontium titanate example is not a quantum material, so let's look at some more ruthenides. Here's an important spin triplet superconductor, strontium-2, ruthenium-04. Let's look at what effect pressure or strain can have on this material. Okay, and the pressure effect on strontium ruthenate was looked at many years ago, and although this material is superconducting in the vicinity of 1 Kelvin, and a very interesting material it is, as Laura knows well. In bulk, when you put it under hydrostatic pressure, the transition temperature goes down. Well, that's not the direction that we would like, certainly in terms of your room temperature applications of these quantum materials, or making your quantum computer. We'd like to go up. And so you might think of negative pressure. Well, that's something that's difficult. I challenge the next speaker to tell me about how they're going to do that. But it is something that you can play around with in other ways of strain. So here's work that's used uniaxial strain to try to tweak the band structure of strontium ruthenate. And in this work from Andy McKinsey's group, they've doubled the transition temperature by applying uniaxial strain. And what they think is going on here is that this band is getting closer to the Van Hoff singularity over here, okay, as they apply this uniaxial strain. Strontium ruthenate's a brittle material, so when they hit it, the highest that they could get was to 0.8% strain before they broke their crystals. Nonetheless, they did increase the transition temperature significantly, which is great, but maybe there are other ways to impose even larger strains. And that's, again, where thin films can come in. If you have a very thin film, the volume free energy associated with straining this thing is quite small. So you can strain to much larger amounts, so percent levels, and I'll show you that right now. So on this kind of a number line like I was showing you before, if we look at where bulk strontium ruthenate is in terms of its lattice constant, it's over here. And if we look at Andy McKinsey's strained strontium ruthenate, okay, he's strained it slightly uniaxially like this. But we can think of all sorts of bulk crystals to rain down the strontium and ruthenium on top of, in terms of changing the properties of the strontium ruthenate. So in this example, here you see our unstrained strontium ruthenate in ARPAs, and here you see the strained strontium ruthenate in ARPAs made possible by this approach. And I hope it's clear that you can see this band getting closer and closer to the Van Hoff singularity over here. It hasn't quite gotten there yet, so we want to put more strain on it. This shows the power of being able to see the band structure. Before, I showed you McKinsey's result where he thought, based on calculations, that he was getting closer. Here you can see that's what's going on. And you can imagine, more strain, we might get close to the Lifshitz transition. as what was an electron pocket around the gamma point turns into a hole pocket around the X point. But we need more strain to do that. And the way that we've done that is we've used a combination of substrates and chemical strain. So we switched from strontium ruthenate to barium ruthenate. Okay, now you might think, well, why is it doing that? Well, it's because we first tried strontium ruthenate way over here on these the next substrates in our series from the single crystals that are available commercially. And when we tried to put strontium ruthenate on top of these substrates, it relaxed basically immediately. So we said, okay, let's try using chemical pressure. And barium is also capable of stretching apart that ruthenium oxide plane. So that's what our game is here. We want to make the ruthenium oxide plane even further apart. So in bulk, those of you that know the ruthenates, barium ruthenate, Mr. Gibbs, or Professor Gibbs, it has a lower free energy phase. It doesn't have the same relative copper n equals 1 structure. But using epitaxial stabilization to a perovskite substrate, you can make it go down in this structure, and then you can start to strain it. And I'll show you what happens to the ARPLES result. So here is in terms of thin films on these two substrates, we can stretch the ruthenium oxide plane even more by huge values, over 2%. And it's in access through epitaxial stabilization, this metastable polymorph of barium ruthenate. And this shows you the band structure. So I showed you before comparing strontium ruthenate that's unstrained. Here we're straining it. Okay, we're getting closer to the Lifshitz transition. Here we've gone past the Lifshitz transition by straining the ruthenium oxide plane by more than 2%. What was an electron pocket here has turned to a hole pocket over there. Okay? Here you can see a series of substrates. And you can see directly, this is the energy axis here, but you can see directly this band, which goes from being below the Fermi level to being above the Fermi level. So you can see as we traverse that Lifshitz transition and change the band structure of the material, our theorist colleagues see that there's something very interesting in terms of TC. This vertical axis here, I'm told, is somehow related to TC. In units that only a theorist can love. But as we're going along the strain axis, that indeed the transition temperature should go up drastically as we get close to this Lifshitz transition. Well, this is an opportunity. We need to have cleaner films. Okay, maybe I haven't pointed that out. Our films are not superconducting yet. Okay. But the opportunity to combine this approach between using single crystal substrates and films, I think, is enormous to access hidden ground states that have better properties and provide theorists with meaningful feedback. So I've said this in different ways. Imagine being able to tune quantum materials. So today, maybe there's an interesting quantum material that lives over here in some simplified axis space. And you think of, okay, that you have this material, and maybe you have other materials, and you're looking around for one that has incredible properties. Imagine instead that you could start with a material and tune that material in a controllable way. So by that tuning, I'm talking about, in these simplified axes, I'm talking about strain or changing strain on this axis, okay, or carrier density on that axis. But there are many other axes that you can imagine. And these axes come from having this control of a substrate together with a film. But it's important not only to alter the ground state, but also to be able to see the electronic structure and provide that meaningful feedback to the theorists. So this imagination, I think, is all about breaking the rules when it comes to quantum materials. And if I were now to summarize what I think the opportunity is, I think that the fact that thin film people and bulk synthesis people tend to be separate communities is true not only in our country, but it's true around the world. And I think that's a huge opportunity for the United States. If that, if we can actively enable those two communities to work together and access this much larger space of quantum materials. I think that that's a huge opportunity for the country. So in terms of the opportunity that I hope that could be possible from this instrumentation program, it's really to empower our country to explore this vast space in a meaningful way. I also have a challenge for the theorists. So there's been a huge push in our country for the materials genome and what I would call materials by design. Which doesn't work terribly well for these highly correlated materials. But that push to figure out where to put the atoms to get those stellar properties can be greatly enhanced, and it's a huge challenge, by taking it a level further. Not just where do you want the atoms to be, but help us synthesis people figure out how to get them in those desired locations. What's the energetic pathway that we should follow for their synthesis? What are the competing ground states that we have to contend with? I showed you the simplified diagram in the beginning from Praveen's work of how we want to stabilize one of these ground states. Well, what are the other competing ground states? How can we destabilize those and stabilize the one that we want? That's a huge challenge for theory. And I think that this is an area, in terms of getting the structures right and the energetics right, that's where the theory could help us today in terms of the synthesis of these quantum materials. So I'm not saying that this is going to be theory-led here, materials by design of quantum materials, but I'm rather saying that there's a huge opportunity for theory to help us with the synthesis and the design of these quantum materials. And it's a huge challenge. So to make that more specific, what are the competing phases? And I'm not just talking about the phases that are in ICSD. I can see those. I want to know what the other ones are. So imagine you put the same stoichiometry in a box. What are the low energy structures that could come out of that? Compute the relative energies. Compute the convex hull. Construct the relevant phase diagrams. All these things are infinitely helpful to synthesis people, whether they're bulk or thin film. And then help identify a pathway to actually make these things. Okay. So I've said, a lot, it's been very quiet. But no tomatoes yet. I've said a lot about what I think an opportunity is, and I want to make it clear that I think this opportunity, it's imperative to have a team effort. There are so many diverse aspects to this, not only in the synthesis, bulk and thin film, but also in the theory and the characterization and the giving the feedback to the theorists in terms of the electronic structure. That it's important to not just have a result and throw it over the fence, but actually to work together. And that's the only way to accelerate this. So I said that on all those levels. If we get closer to what kind of equipment could make this possible, in terms of mid-scale instrumentation, I think there's a huge opportunity on the synthesis side to not just make floating zone crystals, which could be great, new states of matter, great substrates, but actually to make them in larger form, to scale them up. They can be relevant to thin films, where sometimes you need to have the high perfection of the substrate. So these two techniques, this is terribly funded in this country, coupled with thin film synthesis. Okay, now I happen to have a particular, we all have our particular favorites of thin films, but there are many great ways to make thin films. But I think it's key in making those thin films, particularly of quantum materials, to couple it with in situ measurements that give useful feedback to the theorists. So I've shown you, some examples here of electronic structure, but there's even better ways to do this. So for quantum materials, we'd like to see this, spin resolve, like to see this time resolve, like to see this spatially. Lean has huge opportunities. Okay, well, anyway, I'm done with my talk. I was just offering a perspective on where we could go with this, and the key thing is to break the rules and to form highly interdisciplinary teams targeting quantum materials. Thank you.